Okay, I don't see Andrew or Colby. Okay, last day of the week. We are going to talk some more about energy, and then we'll start talking about momentum. So, getting right into it, we had the pendulum last class period. As we said, I broke my bowling ball, the screw actually, so we weren't able to use the bowling ball. But I wanted to go over, because sneeze, I'm sorry. I hate when that happens. Okay, I wanted to go over the energy considerations with the bowling ball swing. Because it turns out when we're solving problems in dynamics, which is why things move, you have really two approaches that you can go. One is what we've learned with forces and Newton's second law. The other one is using work energy. Now, work energy has a really nice advantage over using Newton's second law, and that's because work doesn't have a direction. Energy doesn't have a direction. What do we call quantities without direction? Scalars. So work and energy are scalars. It's easier to deal with those than it is to deal with forces because they're vectors. So if we're trying to solve a problem about what happens with the pendulum swinging, we, of course, as I said, we have to decide where our reference point is going to be for elevation. That's an arbitrary decision. That's up to you. For convenience, for a pendulum, we always say that the height is 0 at the lowest point. And then any point above there, it has a positive potential energy. If we had set the top was at 0, then it would have just gone to negative potential energies as it went down. It may seem wrong because potential energy means the ability to do work. So negative potential energy sounds like it doesn't have potential to do work. But in fact, all that's important is the difference in potential energy. So the fact that it's a negative number isn't a key thing. We could have also chosen like the top of the pendulum to be the 0 position. It still would have had the same output. So we have to define where we're going to consider 0 for elevation. And then we just take any location, we say, what's its kinetic energy? What is its potential energy? So for instance, at this point here, we say, okay, it's at height h, so it has potential energy of mgh. What's the kinetic energy of the ball when it's at its highest point? 0, right. Because kinetic energy is 1/2 mv squared. You see at the bottom of the screen there. So the kinetic energy initial is equal to 0, and the potential energy initial is 0. Now, this graphic is really trying to oversimplify it. Total energy is equal to kinetic energy plus potential energy. So at this point, the total energy is 0 plus the potential energy, right? Kinetic energy is 0. Potential energy is mgh. And so they didn't put 0, kinetic energy plus potential energy because the kinetic energy was 0. But that's what they did. They added up both. So it starts with the total energy of mgh. Then as it drops, assuming there's no air resistance, we're going to have all of the energy, all the mechanical energy, remaining the same. But it can shift from one type to another type of mechanical energy. So potential energy, gravitational potential energy, was one type of mechanical energy. The other type of mechanical energy that we're dealing with in this problem is kinetic energy. So these are all mechanical energy. So that's not including things like chemical energy or thermal energy, where we're specific types of energy. With no air resistance, we're not going to have any loss in mechanical energy. Remember, conservation of energy. Energy can't be created or destroyed, period. But it can be moved from mechanical energy into another kind of energy. And so if we had air resistance, which of course we did with the actual pendulum, you saw that it did not come back up right to the chin. That air resistance is not removing energy, it's removing mechanical energy and converting it into another kind of energy. So in this case, mechanical energy will be conserved. That means that no energy is being put into a different type. So at any point, the total energy is still going to be kinetic energy plus potential. Down here at the bottom, what was the potential energy at the bottom? Remember, what was the first thing I did on this entire slide? I set my reference point for 0 is at the bottom of the swing. So the height is 0 down here, and since potential energy is mgh and h is 0, the potential energy down here is 0. And the kinetic energy is 1/2 mv squared, where v is going to be the speed here at the bottom. Now if I take these two and relate them, my energy initial was kinetic energy initial plus potential energy initial, which was 0 plus mgh. My energy 1, I called it 1 there, is equal to kinetic energy 1 plus potential energy 1, which is 1/2 mv1 squared plus 0. And if mechanical energy is conserved, what can I say about those two mechanical energies? What does conservation mean? Ruh-roh. Should have made sure that one was clear. In physics, if something is conserved, that means it does not change. So if mechanical energy is conserved, then mechanical energy is not going to change. So if I start with mechanical energy of mgh and I end with mechanical energy of 1/2 mv squared, what can you determine from those statements? They have to equal. So what I'm going to be able to do is compare my starting with my ending. So I'm going to have the mechanical energy initial is equal to the mechanical energy at the bottom, which gives me mgh is equal to 1/2 mv1 squared. And now I can immediately calculate how fast it's going to be traveling at the bottom based on where it started. So multiply both sides by 2 and divide by m. Notice when I divide by m what happens. The m's cancel. Thank you, Denford. The m's cancel out, so you don't have any m anymore. Multiply both sides by 2. So 1/2 times 2 disappears. And I have v1 squared is equal to 2gh. If I square root both sides, then I get v1 is equal to, of course, technically plus or minus, square root of 2gh. So I find out how fast it's traveling at the bottom based on how high it started. Now I could use this same principle for somewhere in between. Let us suppose that I have this position that is going to be h2 is equal to the total h divided by 2. So when it's dropped to half of its height, I can find out how fast it's going there in a similar fashion. What were the steps that I did in the problem I just did? I did in the problem I just did. What are the steps that I went through? Step 1. Not feeling like there's a lot of buy-in on this process. Step 1 was identifying the energy I started with. So I'm going to start for the same thing. So I'm still going to have that for step 1. Step 2, what did I do? The energy at the bottom. Now in this case, instead of going to the bottom, I'm going halfway down. So I need to find the energy there. So I'm going to calculate what energy 2 is. So I have kinetic energy 2 is 1/2 mv2 squared. I don't know how fast it's traveling there, so I have to write the full-on equation. And potential energy 2 is equal to mgh2, which I said was mg, and h2 was h over 2. And so the total mechanical energy at position 2 is the kinetic energy plus the potential energy. Now that I have that, what was step 3? Set them equal to each other. So now I simply set them equal to each other. So I'll have the energy initial is equal to energy 2. So mgh is equal to 1/2 mv2 squared plus mgh over 2. Well, I want to solve for v. So if I want to solve for v, I'll have to subtract mgh over 2 from both sides. And what that leaves me with is 1/2 mgh equals 1/2 mv2 squared. Okay, you guys all have a reasonable amount of math, right? There's a requirement. How do I solve this for v2? Okay, I'm going to have to divide both sides by m and multiply by 2. Divide by 1/2 or multiply by 2. What I do to one side, I must do to the other. So I did it on both sides. 2 times 1/2, that cancels. M over m cancels. And I'm left with v2 squared is equal to gh. So v2 is equal to plus or minus square root of gh. So I'm able to find the speed in a really quite simple fashion. Find the energy I start with, find the energy I end with, and set the two equal to each other. As long as I don't have something like friction that would take my mechanical energy away and put into something else like heat. In that case, well, then it becomes a little more difficult. I have to calculate what that is as well. Now, in this picture here, I went to this picture. I didn't remove it for one reason only. And it has nothing to do with this stuff here. I mean, true statements, but not what I want. When you look at this picture, it's a confusing picture. It's an ill-devised picture, in my opinion. What are the arrows in this picture? Okay, Denford, I heard you answering. Okay, so this here is the force of gravity. What else? Okay, so the force of tension. And there's no force in that direction. That's not a force. That's the velocity vector. Way to confuse us, right? And so I wanted to bring this out so people can look and think about these ideas. You know, don't make it so it looks like you have 3 forces when you only have 2. Right? That's a bad call. Now, maybe they're saying, what if you're pushing it? But there's nothing here that says if you're pushing it, right? It just says like this. Now, I'll tell you what it really is supposed to be. It's supposed to be that this is the force of air resistance. So it's swinging like this. It's supposed to be that's the velocity direction, and it has air resistance. And in that case, the air resistance is going to do a negative work and take away energy. But when you look at it, you don't see that, and you really have to make sure your figures are clear, because otherwise, yeah, it looked like it was just the velocity. So I want to make sure people understand about the figures. Now, I know on the tests, multiple choice questions, I'm not grading you on your figures. But if you want to get the questions right, a figure usually helps you to solve a question that has forces in it. And if you can draw a figure that's going to help you solve, that's to your benefit. All right, our first clicker question. Give me a second. A lever is used to lift a rock. Will the work done by the person on the lever be greater than, less than, or equal to the work done by the lever on the rock? Now, assume that unlike the picture illustrates, the rock is just going to stay on the lever. Right? Because, I mean, in real life, you would just tip that rock right off. But assume it's going to stay on the lever. And that the fulcrum is perfectly stable, is not going to roll either. Okay. This goes back to lab on Monday. So take a few moments to discuss with your nearest neighbors what you think the correct answer is and why. Okay, let's re-poll this. And so it's open now. Everybody's in. Hooray. I heard arguments for the wrong answer, but everybody moved toward the right answer. That's good. Equal to is the right answer. All but one person should be nodding their head now. Right? Now, this is assuming an ideal situation. A lever is pretty ideal. This is what you did in lab. What did you find for the efficiency in lab? Is what? High 90s. High 90s. What did you find for, well, yeah, not the mechanical advantage. The efficiency, we didn't actually work it out this way, but the efficiency is really giving you this ratio. The ratio of the work you put in to the work that you got out. And that efficiency ideally is 1. In an ideal situation where you have no friction, no air resistance, the work you put in is equal to the work that the machine does. So if the work is the same, what was the point of the simple machine? Okay, change direction is part of it. Depends on your simple machine how you're going to change direction, but that's part of it.
More work with less force.
Okay, not more work, but you do the work with less force. So the key here is that you apply less force for the same work. Now remember, work is equal to the force parallel to the change in position. So if the work is the same for both sides, but you put in a lower force, what does that mean the delta x is going to have to be? The distance you move. It's going to have to be higher to achieve the same work. So you're not getting something for nothing. It's not a, in physics, we would just call that a magical device, not a physical device. But it's making it easier to do the work. Easier because it requires less force. Okay, this is actually our last slide on energy. This is a simple example of a very good sister pulling her little brother up to the top of a hill. She has to do work. If she goes up 20 meters, and if her brother has mass equals 40 kilograms, can you tell me how much work she had to do to get him to the top? The answer is supposed to be yes. So think about it. Can you tell me? So now I've gone from is it possible to can you see how you can determine it? You don't have to know time. Time relates to the power, but not to the work. Okay, here's how. Remember we learned that work was equal to the change in kinetic energy? Now that's really the net work. So when I wrote it down, I said I'm going to write net in here. So it's the net work is equal to the change in kinetic energy. Now if her brother starts at rest here, so he starts here with V initial equals 0, and gets up to the top and he again has V final equals 0, what's his change in kinetic energy? His change in kinetic energy is going to be 0. So this is going to be 0 for the net work. And now we say, uh-oh, if it's 0 for the net work, then how can I calculate how much work she did? Well, what forces were acting on the boy? That was not what I wanted to do. Okay, gravity is one of them. In what direction does gravity always point? Down. Okay, that was a yawn. I thought you said up. So we had force of gravity equals mg down. What other forces? Okay, there's the force of tension that's already marked here. I'll put a little T for tension. And then there's one more force. Normal, which points what direction? Away from the surface. So we have force normal like this. Now we look at the work done by each of those forces. We had the force normal. How's the angle between the force normal compared to the angle of the motion? Not just about. It's 90. Because the normal is by definition perpendicular to the surface, and as long as she's not yanking him off of the surface, he's moving parallel to the surface. So that means the work done by the force normal is equal to 0 because force normal is perpendicular to the change in motion. And it's only the parallel parts of the force that do work. Now, if we look at her pulling, well, her force is parallel to the distance, but I gave you no information about what the distance was, or for that matter, what the force was she has to pull with. You would have to know the angle to be able to calculate the force. But we can look at gravity, the work done by gravity. What direction is the force of gravity? I've already asked this, but now it becomes very pertinent. What direction is it? Down. So if gravity is down, what part of the motion is parallel to gravity? The upward, because it's technically anti-parallel, but that's in the same direction. So the work of gravity is going to be the force of gravity, mg, multiplied by the change in height with one thing. Force of gravity was down, the change in height is up, so that's going to have a negative sign. And so now we can take this and say, okay, my work net is equal to the work done by the force normal plus the work done by gravity plus the work done by the sister, and that's equal to 0. And so work done by force normal was already 0. So I can put minus mg delta h plus work done by sister equals 0, or the work done by sister is equal to mg delta h. So I know the amount of work she's going to have to do to get him to the top is just his mass, which I said was 40 kilograms, multiplied by g. To make my life easy, let's use 10 meters per second squared here. So multiply that by 10, so that's 400. And then multiply it by the change in height, which is 20 meters. 400 times 20 is 8,000. So this is equal to if I put all the units in ugly fashion, that's kilograms times meters, so meters squared per second squared. What's the simpler way to write those units? Joules. So I was able to calculate the work she did to get him up there. Now you notice the work she did was just equal to the change in potential energy. Well, minus the change in potential energy, because change in potential energy should have been final minus initial. So her work goes into the change in the potential energy. We actually define potential energy. This is the definition of potential energy, the true definition. The 3 lines mean is defined as. Minus the work done by conservative forces. As far as we're concerned, that would be by gravity or by a spring. And so if you knew that already, you could have answered that way. You didn't know that already, now you do. But we were able to use the principles we've already learned to calculate how much work she had to do. Now when she did that work is changing the energy. So the change in energy, that's not an E. I just have to tell you, we've been studying voltage in my other class. Voltage, also known as electric potential, is potential energy per charge. And so I started thinking about the voltage. The change in energy is equal to the net work. And so when she pulled the person up, it's changing kinetic energy's network. That's wrong. What was I thinking? Yeah, she did. Yeah, I should have written it this way. The change in energy is equal to the change in potential energy plus the change in kinetic energy. And so this was the work conservative here, the change in potential energy. The work done by the girl was non-conservative, and that's what I meant to write. The work non-conservative, that's the work done by friction or work done by a motor, or in this case a sister pulling, is equal to the change in energy. That's what I meant to write. And so she changed the energy by doing a positive work, adding energy to the system. So up here, the total energy is mg times the height of the hill. What happens when the boy starts sliding down? It's going to be converted to kinetic. So let's say he gets here. He's sped up some, right? What happens to his speed going from this position to that position? Slows down because kinetic energy was converted back into potential energy as he went up the slope. But then he comes down here at the bottom, and we can use the energy ideas we did earlier to calculate the speed at any point. Take the energy he had right here, compare it to the energy he has here, and you can determine what the speed is. And so that's actually, there's supposed to be like 4 or 5 clicker questions here asking about what the speed is going to be at this point and at this point. But we're not going to do those. Any questions on these work energy things? Okay, I am going to do my first demonstration here just because it's kind of fun. Okay, this here is essentially half of a racquetball. So I take the racquetball and I flip it out. Now, did I have to do work to flip it inside out? Yeah. So now I'm going to take this and put it on the table. Put it on the table. And it shot up in the air. In terms of energy, why did it shoot up in the air? When I did my work on it to stretch it, I was storing potential energy, elastic potential energy in this case. It's acting like a spring. And then what happened, Andrew? Then it released it, it snapped back into shape. And so that potential energy was converted into kinetic energy. Also, it was converted into other forms. You heard it, right? That is also a form of energy, acoustic energy. So some of the work I did was converted into the sound you heard. Some of it was converted into kinetic energy. It slapped the table. It pushed down the table, according to Newton's third law, had to push back with equal and opposite force that propelled it up to the sky. As soon as it left the table, then what started happening? Okay, it was accelerated by gravity. What do you say, Jeffrey? Speaking in energy terms, its kinetic energy started being converted into gravitational potential energy as it went up. So as gravitational potential energy went up, kinetic energy was dropping. Got to the top, what kind of energy did it have at the top?
Potential.
Just gravitational potential. But then potential energies will give the energy back. And so that gravitational potential energy was converted back into kinetic energy and it came back down. Now that's my first demonstration. The second one is kind of similar. We're going to start talking about momentum, and I'm going to start by dropping some balls. So I have two balls here. Tyler in the front row. Compare the two balls.
This one's heavier.
Okay, he says one is heavier. They're actually supposed to be the same mass, but I think you're right. Okay, this one's a little heavier. One thing that I want you to check after we do this is what happens when you squeeze them. I'm going to take these two balls and drop them. What will happen? Should land at the same time. That part was true. But this one bounced nicely and this one didn't at all. Why not?
Different material.
They're different materials. So now come back, squeeze them, and describe how they respond when you squeeze them. Can you compress both of them?
This one doesn't compress. This one does.
Okay. This one is hard to compress. You can compress it, but it's harder than this. Well, not a lot harder. But one of the really key things that you notice if you're really careful, this one when you compress it, when you release, it comes right back with your fingers. This one when you release, it doesn't. It takes a little bit of time for it to come back. For something to bounce, it comes down, it deforms when it hits the surface. It's converting that kinetic energy into compressing essentially the spring. And then that spring uncompresses, energy that was stored as potential energy is returned. This one gets compressed, but it slowly comes out. It returns energy really slowly. Well, that's not enough to throw it up in the air. This one returns it really quickly, throws it up. So one of the things we talk about with bouncing objects is the coefficient of restitution. What percentage of the energy is returned? Now, I want to go straight to some YouTube videos here because they're actually really interesting, I think. Boom. I believe this will play. If it doesn't, I just have to reload it. So here's a ball bouncing. Unfortunately, that red line, or white line, kind of obfuscates what happened there. So let's go back. What's happening? Okay, I'll start here. What's happening to the balloon as it hits the floor, or the ball? It's compressing, and you can actually see some cool waves that actually go up through. You can see waves going up through the balloon. So there's very interesting things going on in terms of how that rebound occurs. And the rate at which the waves go through is really important. Okay, don't want to watch that one. Just going to close that window. A lot of us grew up playing baseball. When you hit a baseball, you just generally think, I have a bat, I hit the ball, the end, right? That's as far as we go with it. But have you noticed the size of a bat is different for a baseball compared to a softball? You ever wonder why? The reason is you want the time for your bat to compress and rebound to match the time it takes for the ball to compress and rebound. So because you have different balls, you need different bats to make those times match. Why do you want the times to match? Because if the times match, you're going to get the most transfer from the bat to the ball. And so there's actually a lot of science that goes into designing bats that are going to be more effective. Now, there's also aspects like the bigger the barrel, the easier it is to hit the ball, right? If the barrel was this big, it'd be really easy to hit the ball, except for air resistance would be really an impediment. Now, this young lady's video, I think, is top-notch.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm going to try the golf ball on top of the bouncy ball, on top of the basketball.
Before she does it, I'm going to do it. I can't let her steal my thunder. I have 3 bouncy balls and then a 4th bouncy ball. I can do this at the end. She'll say why she can't. I'm going to drop it. What's going to happen?
The little bounce ball shoots straight.
Okay, we got a prediction. Okay, the little bouncy ball shot up way higher than I dropped it, way faster. Why? That's right. When it hit, the first thing that hit was the bottom of this ball. And then that sent a wave through this ball, and when that wave hit this one, that's when this one knew it was bouncing. So the bottom one started bouncing before this one, but then that wave transfers through this one, which transfers through this one, and you have a lot of the energy from all 3 of these balls gets transferred to the last one. And so it goes shooting off. Now she's going to explain this real nicely, but I had to do my demonstration first, just because if I don't, you're just going to be so disappointed with mine.
How it's related to a supernova.
Pretty awesome, right?
Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these 2 balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
Okay, I thought that was pretty darn good. Let's not look at their grades. Instead, let's come back to this. Okay, now that is in my slides a little later, but I just wanted to make sure we did that before I forgot. There is a little section at the end of chapter 5 that to me seems a little bit out of place, but this is where it's introduced because it has to do with energy. If you have a block with some mass m, and you attach it to a spring and you pull it back, in terms of energy, when you pulled it back, you did work on the spring. And so that spring stored energy, what do we call that stored energy? Potential energy. And we saw in class, the end on Wednesday, that the potential energy for the spring is 1/2 K times the amount the spring is stretched squared. So we have potential energy in that spring. If you let go, what's going to happen? It will compress, it will come back to its equilibrium, returning that energy from potential into what kind of energy? Kinetic. So when it's at its equilibrium position, here the potential energy of the spring is 0, and you have all kinetic energy. Here the kinetic energy was 0. You start from rest. But because it's moving, it's going to keep moving. We learned about the law of inertia, that things tend to go unless a force acts on them. So its momentum, the topic we're coming to, is going to make it keep going, and it'll compress the spring again. So when it gets back here, all of that kinetic energy has been converted back to potential energy. How is the amount it's compressed in the end going to compare to the amount it was stretched to begin with? Remember, the kinetic energy here is going to be back to 0. So if you start with all potential energy, you convert to kinetic, and then you convert it back to potential, how's that potential energy going to compare to the potential energy you started with? It should be the same amount of potential energy. Now, this would be compressed instead of stretched, but the x, the distance it's compressed, squared, has to be the same as the distance it was stretched squared to begin with. And of course, at this point, what's going to happen? You have potential energy. What's the spring going to do? It's going to return it, and it'll come back the other way. So it's going to oscillate back and forth. With this oscillatory motion, we can graph the position, that is how far it's displaced from the equilibrium position, the position where the spring would be if you didn't do anything to it. And you see that it's oscillating back and forth. We call this kind of motion simple harmonic. So when we get to talking about sound, we'll talk about this motion a lot more. That's why it seems kind of out of place, because we're not talking about sound right now. Some important parameters we use to describe oscillatory motion like this is the period, the time that it takes to do a complete cycle. So the time to go from completely stretched to its equilibrium position, to completely compressed, back to equilibrium, back to stretched. That's the time for one cycle. We call that the period, and it has the symbol T for period. So period has the symbol T. Frequency is related to period in a very simple fashion. Frequency is equal to 1 divided by the period. The frequency is how many times per second it goes back and forth. And so we talk about frequencies a lot. The frequency of the electric power coming out of here is 60 cycles per second. That means that the electricity goes to its peak positive value, back to negative, back to positive, and does that 60 times in 1 second. We actually have a new unit. 1 hertz is equal to 1 cycle per second that we use to make it easier to describe frequencies. So instead of saying this is 60 cycles per second, we usually just say it's 60 hertz. When you're in choir and you're doing a concert A, I think a concert A is 440 hertz. It might be 400 hertz. I'd have to look at it. But we just say it's that many hertz, that many cycles per second. If you're singing, that means that these little vocal cords are flapping back and forth, open, close, 400 or 440, whichever one it was, times per second to make the bursts of sound, the bursts of air pressure coming out. The amplitude is the maximum amount that you move from equilibrium. So with my example here with the spring, the amplitude was this distance, the maximum amount that it moves away from equilibrium. And it's the same whether you're compressing or stretching. So if you look at this graph, the amplitude is the same going up or down. So those are things that we're going to come back to later that are introduced here because they have to do with the spring and the energy. So I am going to leave those and start talking about momentum very quickly. Momentum has a lot to do with collisions. But I am going to start by defining momentum and talk about some simple situations. So we've looked at a ball bouncing. We have the question here, what happens when the ball bounces? The ball's velocity initially was downward. When it hits the ground, what happens to the velocity? It goes from downward to upward. So the velocity is changing pretty significantly. Momentum is very tightly related to velocity. Specifically, momentum is mass times velocity. That's pretty long to write. So we write it in a much shorter fashion. Now you know mass and velocity already. So by process of elimination, you know what symbol do we use for momentum? P. P for momentum. Why? I don't know. Right? There's obviously no P in momentum. But that is the symbol we use. What does the arrow on top mean? It has a direction. Okay? I've got 1 minute left. I can totally do this. Newton's second law says that the net force is mass times acceleration. But of course, acceleration is change in velocity divided by change in time. So I can rewrite this as if the mass is constant, the change in mass times velocity over change in time. But what is the mass times velocity from the previous page? Momentum. And so Newton's second law, and this is actually the correct form of Newton's second law. Well, the correct form is a differential equation. But the most correct you're going to do without calculus the sum of the forces, or as written here, force net, is equal to the change in momentum divided by the change in time. That's actually the most correct, without using calculus, form of Newton's second law. The mass times acceleration is only true if the mass is constant, which for all of our cases is true. Now, why is this important? I can take this equation and I can solve it for change in momentum. Change in momentum is the net force acting on an object multiplied by the time over which that force was acting. Now, we are out of time, since that word just came up, so I will on Monday begin talking more about momentum, and yeah, that's it. So have a great weekend.